I'd like to thank I'd like to thank the organizers for inviting me. It's an honor to be present at the first International Knot Theory Congress in honor of Lewis Kaufman's 80th birthday. So I'll be talking about various ideas relating to knots in a distant way, in a sense. These ideas were motivated by numerical computations on fluids. This is an ongoing long-term project of Dennis Sullivan over the last 3 decades, maybe. Particular work we're talking about today is joint with Daniel Ann of Aaroni and Dennis Sullivan, and supported by the BSF. So let's talk about the idea of discretization. So if we think about Navier-Stokes equation, so here's a Navier-Stokes equation for incompressible fluids, a PDE, so we have functions of space, these U's, the velocity field and the pressure term, and they're functions of space and time. If we want to discretize, in order to put something like that on a computer, you have discretization both in time and in space. If we think, first of all, about discretization in space, you're turning your spatial dimension into some sort of a lattice, and the velocity field will be defined as a function of time at lattice points. And the partial derivatives in spatial directions, you might think, would be turned into divided differences, ordinary divided differences or symmetrized divided differences. The problem with that is that different equivalent forms of the continuous equation tend to discretize into inequivalent systems. So I've written down 2 typical forms, well-known forms of the Navier-Stokes equation here. One's known as the convective form, the other's known as conservative form. Details don't really matter. The point is that they are equivalent via some vector analysis identity. And at the bottom of the vector analysis identity is the formula for differentiating a product, in other words, Leibniz. Leibniz will hold in a continuum setting, but not in a discretized setting, and that's the core of a problem. So, for example, if I just write it down in the simplest form for a derivative being chosen to be this divided difference, then this equality does not hold. You can fix it. So these are different ways of fixing it. This would be this discretized form of the derivative of the product. This is what you would think of as f tag g plus f g tag. If I alter this g to g of x plus h, then it holds, but now we lose symmetry. You could write it like this, that would also be true, or you could just admit that you don't have an equality and there's an error term and add on the error term. Any way you do it isn't quite perfect. So in a sense, here, if we do it this way, we are missing symmetry, which would turn into commutativity. If we do it this way, we're missing Leibniz, and then there's a third way of doing it where you miss associativity. So none of them work perfectly. In order to try and understand the situation a little more intelligently, let's try and use some ideas of algebraic topology. So let's start again. Here are our equations. Instead of thinking of U as just a function of space and time, we'll think of it as a time-dependent differential form. So now we have the time derivative, and we have operators in differential forms. We have exterior D, wedge product, and star. And now the properties of associativity, graded commutativity, and Leibniz tell you that we have a differential graded algebra here. So that's all very nice, only that if in order to do numerical work, you need something finite dimensional, and space of differential forms is not going to be finite dimensional. So we need some sort of an approximation. Okay, so here, just to illustrate the problem again, so I've just written out these properties formally. So according to folklore, it's impossible to construct a homologically faithful finite dimensional algebraic model of differential forms, which preserves all 3 properties of graded commutativity, associativity, and the Leibniz rule. So typically one goes about this by producing a quantization of spatial algebra, which is suitable for the purposes one needs, by starting with a finite dimensional model which lacks one of the properties, and then you somehow add terms to correct the error, and you end up with an infinity algebra of some sort. You can either think of it as an infinity algebra or a sequence of approximations in some sense with quantitative estimates in the best case on the error terms. But we don't really want to go down that avenue. That's something that we have done with Dennis Sullivan in the three different directions here. We've produced such models, but that's not what I want to talk about today. What we want to do is to have it always, to somehow keep graded commutativity, associativity, and Leibniz, and also keep finiteness. Now, of course, since that folklore result holds, something is going to have to be given up. And what will happen is that closure is given up in some sense. But we'll have just enough to be able to get by to write down Euler's equation. Okay, so let me go back to illustrate what's going wrong again from a slightly different point of view. Instead of thinking in terms of differential forms, let's look at it, well, I guess it's the same thing in terms of cochains. So what happens at zero cochain is a function on vertices, and one cochain is a function on edges. Multiplication on zero cochains is no problem at all. You're just multiplying pointwise, and that is fine. As soon as you try and multiply a zero cochain by a one cochain, you want to get a one cochain. So if we think of simplest system, you have an interval, an edge, two vertices. You have, say F was a zero cochain, G was a one cochain, and we want to define the product, and we want to define its value on the edge E. So it should be, well, you need F only takes values at vertices. So you have to pick either A or B and multiply it by the value of G on E. So that's already asymmetric. Of course, you could take the average, and that would make it symmetric. So here we could do it the other way around, which is like this. And so you have the problem of choosing essentially a cellular approximation to the diagonal. It's exactly the same problem. So we can either choose it to be one way round, which is not commutative, but it is associative, and this is the Alexander-Whitney-Cup product. You could take the opposite multiplication, which similarly is not commutative, but is associative, or you could take the average, which by definition is now commutative, but it won't be associative. And there's another story. So here I'm writing the same thing again, but it could be in higher dimensions. Another story appears if you take edges of length 2h, you could take the value at the midpoint. So that is commutative and associative, but you'll find you've lost Leibniz if you write it down precisely. So anyway, you have to miss something. Okay, so now I'll mention Dennis Sullivan's lattice model of hydrodynamics that he introduced in 2018, where he was using precisely a discretization with edges of length 2h. So all the chains involved were of length 2h, which means they have a nice center, and you can multiply at the center. That's the advantage. The disadvantage is that you won't have Leibniz as it stands. So these no need to understand the precise notation. The idea is that here are two different discretizations. They follow the equivalent formulations of the continuum model of the Euler equation using natural operators on the level of chains. So yes, we've got a co-boundary here, and then we have some other objects which I won't describe, but are relating to various combinatorial bijections that exist in the system. So we can write these down, and one of them, which was called the vorticity model, does allow, proof of exact energy conservation and vorticity also, and therefore it numerically converges better than the other model. These two are inequivalent, although they're both in the continuum limit equivalent to the Euler equation. I guess Navier-Stokes here because there is a viscosity term. Okay, so that is what happened with the more traditional models. Now we want to do something different. So this is just saying the same again about the different models, and we can do the same in higher dimensions. So what we want to do is have something that is commutative, associative, and Leibniz, and keep finiteness. at least, as I say, for our purposes. In other words, we only want to deal with Euler's equation. We know we're not going to get a complete model of the differential graded algebra forms because that's impossible. Okay, so if we're starting with periodic boundary conditions, that means, say, we're dealing with a torus. And the first move is to move from the differential graded algebra of forms to what Dennis Sullivan called fluid algebra. So fluid algebra is a vector space endowed with three structures: a positive definite inner product, a non-degenerate symmetric bilinear form, and an alternating trilinear form. So what does that mean in our case? So we're supposed to think of the positive definite inner product as a metric, the non-degenerate symmetric bilinear form as a linking form, and the alternating trilinear form as a triple intersection form, which means this. So the classical example, we'll take, let's just say two forms for the time being before explaining the top line. We'll take two forms, one forms. Yes, I should have said one forms. The triple intersection product here will be just the integral over the three manifold, in this case, say the torus, of the wedge product. So that's naturally an alternating trilinear form. The bilinear form, the linking form, will just be, you take two one forms, D of one will be a two form, wedge will be a three form, so this makes sense. And it's symmetric by Stokes plus Leibniz. So in other words, if I swap these two around, I have A wedge dB and B wedge dA. And their difference is up to a sign D of A wedge B. And the integral of that by Stokes, well, since M was closed, will be zero. Okay, and finally we have the positive definite inner product, which is this. Okay, now, actually you will find, as we've defined it, that this will be degenerate. I mean, as I said it will be degenerate. In order to make it non-degenerate, you need to restrict to co-exact one forms. So that's what we have here. And then it will be non-degenerate, and that's the archetypal example of a fluid algebra, infinite dimensional. And in this setting, we can write we can write the associated Euler equation, which is an implicit evolution equation for an element of the vector space, a time-dependent element of the vector space, which has to satisfy this condition. So what we have here, as I say, it's implicit. So you think of Z like a test function. The bracket of X dot with Z is this triple bracket. Well, this bracket was the metric. It's a positive definite form, and so given that this is a linear functional on Z, there will be a unique X dot which satisfies this, and this equation is saying that X dot is that unique value. You want to put it in implicit form, an explicit form, sorry, then it will look like this. So, oh, sorry, I guess I missed something here, which was the curl. So if we look at the linking form, it's the integral of m of A wedge dB. So this is star of star dB. So in other words, this is the same as the bracket of A with some linear operator D on B. That linear operator is the curl. Star D is the curl. So you can think of it in this form, and this is the D that appears in here. So the equation here, X is one form, dx is like the curl, that would be modeling the velocity, this would be modeling the curl, and then you're taking a wedge of the two, which will give you a two form. Now you have to take each star, you'll get a one form. And now, well, that may not be in the space we want. We want to preserve, we want to have zero divergence, we want to be in co-exact forms because we have an incompressible fluid, however what you want to say. So we need to project onto this part, the image of D star, part of the Hodge decomposition. So this is an explicit way of writing the equation. This is a much simpler way of saying it, but it's implicit. Okay, so what does this mean? This means that whenever you have a fluid algebra just is a vector space which contains these three structures, no connection between them, then you can write down the associated Euler equation. It will be a quadratic ODE, which you can then solve and will be equivalent to this equation. In the case of the classical example, it is equivalent to the classical Euler equation. So that reduces the problem to finding a suitable finite dimensional fluid algebra which models what we want. So in other words, the structures ought to look like this, but in a discretized form. Okay, so let's see what we can do. So what we'll, as I say, jumped one back. So instead of thinking of differential forms, we'll think about them in the equivalent way as a foliation plus a transverse measure. So we'll be thinking about chains. And instead of wedge, we'll be thinking about transverse intersection. So if you have two manifolds in n-dimensional space, I and j dimensional, then if they intersect transversely, their intersection should in principle be I plus j minus d dimensional. So this picture shows you naturally Leibniz. If you think of this is A and this is B, and the boundaries are what we see here, then the boundary of A intersect B, so A intersect B is this little piece here, its boundary is the difference Q minus P, and they are the intersections. Q is the intersection of alpha with B, and P is the intersection of A with beta, and you can think of those in this way. So this difference is indeed this. Okay. The grading here is by codimension, and the linking number, well, you have to, in the case where, so if here you've got 1 and 1 inside 3 dimensions, then the linking number would just be counting the transverse intersection of 1 with a chain whose boundary will be beta, or the other way round. And why is it the same either way round? Because the difference between the two is a boundary, and the number. So you have a boundary of any union of 1 cells. Then counting them, you will get 0. So that's where you get the symmetry of the linking number from. Okay, so that's what we want to use, some form of transverse intersection. And the aim then is to make a transverse intersection product on a discretized form of space. So let's just start from a torus again. So we'll just be taking cubes and cuboids in such a way that we can reconstruct from that the 3 structure forms of a fluid algebra. Okay, so let's make a transverse intersection product on cuboids. So a cuboid means what the classical definition, a Cartesian product of intervals. The intervals may also be of 0 length, singletons. So then you would have a degenerate cuboid, but it would still be of whichever dimension you desire. And that its type will be labeled by the directions in which it has some size and the minimum, maximum vertices. Okay, 2 cuboids are said to intersect transversally if their closures have a non-empty intersection. So geometrically they intersect, and the union of the types is all of x, y, z. So that means that their tangent spaces span the whole tangent space, or equivalently, their normal spaces are disjoint. So geometrically, so if we have if we have 2 planes, yeah, so they these 2 cuboids, or I guess they're rectangles, which are intersecting transversally. They actually only intersect in a point in this case. But they should intersect in a 1-dimensional object, because this is 2-dimensional and this is 2-dimensional. 2-dimensional objects in 3 dimensions should intersect in a 1-dimensional object. So we have an intersection. It should be 1-dimensional, but geometrically is a point. So that's just giving you an example. Okay, now we say 2 cuboids are in general position if, well, the natural thing. They need to intersect transversely, and every face of x prime of x, y prime of y has to be such that they are either disjoint or intersect transversely. So if you work that out, you'll find that this allows the case that I was just demonstrating. So for example, these are all the intersections of objects which are transversal. So this is a line with a plane, two planes, a point with a three-dimensional object, a line with a three-dimensional object, a face with a three-dimensional object, and two cubes. So these are all transversal intersections in general position. Now, we also would like the product to be such that it is additive. In other words, if you crumble a cuboid into smaller pieces, then it behaves as though this cuboid was actually the sum of the algebra elements represented by the smaller pieces. Okay, and we would like that this transverse intersection product, when intersecting, if I go back to the previous frame, when intersecting any of these, will give the geometric intersection that we see. Exactly. Okay. These intersections are transverse, but not in general position. And so, for example, here we have the two-dimensional objects which should intersect in an object of dimension 2 plus 2 minus 3. In other words, one-dimensional intersection, we see only a point intersection. So, and it should be, in a sense, in this direction. So we need a point-like object in this direction. And in order to do that, we need to add infinitesimal sticks. So there will be this intersection will be an infinitesimal stick in this direction. This intersection will be an infinitesimal stick in the vertical direction, and so on. These will be infinitesimal 2 cells, and these will be infinitesimal 3 cells of various types. So the theorem is that you can do this in an essentially unique way. You can enlarge the chain complex in such a way that the intersection is local. In other words, the transverse intersection of 2 cells will have a support which is contained in the intersection of the supports. It will be graded commutative, where the grading is by the codimension. It will be associative. It will satisfy Leibniz only on the original cells. It's invariant under the symmetries of the lattice. It's non-zero for any basis elements that have an intersection, whose support intersects non-trivially. For basis elements in general position, the transverse intersection is the geometric intersection. And if you count intersections in the case that dimensions add up, in this case to 3, then you obtain a non-degenerate pairing. Note into Q, not into Z. So there will be fractional terms coming in here. And that this structure commutes with crumbling map to a finer complex. So this little condition that the subdivision has to be odd in order to make that work. Okay, and then you can take a subalgebra of this, which is generated by 2 squares of size 2h. In other words, you take the squares of size 2h, you take intersections of such things, which will involve infinitesimal sticks, and then Leibniz will hold without reservation. And it's because of that that we can do Euler's equation perfectly. So what we're left with, in fact, are the original points in the lattice, the original squares in the lattice, and in dimension 1, there will be sticks of infinitesimal length and of length h. That will be our complex. We have nothing in the 3rd dimension, and we have intersections of these, which grading is by codimension. Boundary is a geometric boundary. Boundary of an infinitesimal stick is 0, because it's infinitesimal. Boundary of an ordinary stick is the difference in the endpoints. And here is the explicit form of the intersection here for all the elements. So you see we have 8ths and 16ths, depending on what you want. This is in general position, so this is exactly the intersection here. This is not in general position because these endpoints here are in both. Put it that way, or you can say that this is not the yes. The intersection of these two is not the geometric intersection, which would be this edge here. You have to add on or subtract, if you want to put it that way, 2 little infinitesimal pieces that are at these ends here. And this is forced on you by everything we've said before, by linearity and the condition that on basis elements that do intersect in general position, the intersection is the geometric intersection. Okay, so that's the intersection of squares. This is intersection of one-dimensional with two-dimension. This will be invertible and will provide a essentially a star. Okay, so from that, we can define a fluid algebra. What is it? So again, we're starting with, it'll be a subset of the one-dimensional, sorry, no, it'll be a subset of the two-dimensional objects. Yes. The metric will be, well, you take a face, the star of a face, an ordinary face is just the stick going through the middle. So you take the star, you intersect it with the other two-dimensional object. We just talked about that. This will be zero-dimensional. In other words, points are points. You can add them up, add all the coefficients. This is a number. You have to check that it really is positive definite, but it will be. The linking form will be defined like this. Again, A and B are linear combinations of squares, a boundary of a square. We understand that's the ordinary sticks. These things intersect in an ordinary way. We'll get points again. We can count them. And this three-dimensional one, well, because of the structure we had, this is well defined. In the process of calculating it, you may well have infinitesimal elements. It doesn't matter. At the end, we'll have a union of points which we can count. So all these are well defined. They satisfy the right properties, the symmetry properties. And then you can ask for the associated Euler equation. What does that mean? Well, first of all, we have to define the analog of the curl. What's that? That's how to write this in terms of this. In other words, this is a linear, it's bilinear. So for any particular B, let's say, it's linear in A. And therefore, we can write it as a bracket of A with something dependent on B. That's something we will call dB, the curl of B. And that's how this is defined. I guess an important point I didn't mention, in order to make this non-degenerate, V has to be defined to be this. So again, it is co-boundaries, exact co-boundaries. So you write down the associated Euler equation in this finite dimensional model, and that is what we will want to call discretization of Euler. You can again write it down explicitly, but now you have to define carefully what are these maps. You have the same sort of structure as we had before. That's what you get. So yes, how do we prove this theorem? Well, actually, very simply, the proof of existence is by taking a tensor product of three copies of the one-dimensional solution. So on a circle, one-dimensional periodic lattice, you can very easily check, well, the generating says you only have 0 dimension, 1 dimension, and boundary map, intersections in general position, well, they're what you expect them to be, the geometric intersection. When they're not in general position, well, this will be a new generator, and that then forces everything else. So the unique solution up to rescaling is what we've got here. Yes, and that these XAA means an infinitesimal. So this is XAA plus H. So XAA is just an infinitesimal object at point A. If these things weren't there, then, well, you would have ordinary intersections, and that wouldn't satisfy all the properties. So that's what we have. And the tensor product of three copies gives the three-dimensional transverse intersection product we mentioned. You can do this in any dimension and get a transverse intersection algebra. But then Leibniz will only hold on the original complex. And if you want to truncate, you would have to truncate up to 2/3 of the dimension. So if we're working in, working 3 dimensions for fluids, then we're turning the velocity field into the union of squares by taking the star, the components being on the various faces. So that just works nicely. In higher dimensions, it's not clear what that would correspond to. And similarly, in 2 dimensions, it's not clear how to do 2-dimensional fluids by something of this form. It's a different world. Okay, so the algebra we've generated is this FC star. F here is for fluids. Okay, so to conclude, so we've given various algebraic structures. I guess I really talked about only one, it's this final one, which gives discretizations of spatial algebra. Oh, sorry, where did that come from? Backwards. Sorry. And the last one gave a finite dimensional fluid algebra whose associated Euler equation may be considered as the most geometrically natural discretization of Euler's equation that we have so far. We are in the process of testing it numerically. Because the model comes through a fluid algebra, it comes naturally with exact conservation of energy as well as vorticity. So I guess I can mention that if you look back at the equation. So if we put an x in here, it naturally vanishes because the intersection form is antisymmetric. So that means that x dot comma x is 0. So in other words, x comma x is an invariant. And similarly, if you put dx in here, so x dot comma dx, which is the integral of vorticity. So you naturally have two invariants that come immediately, the derivative of x comma dx, which would be 0. You have two invariants, one being the kinetic energy, and the other being the vorticity, and they should be exact invariants, and that should mean that as a numerical method, it should be more stable than just an arbitrary discretization. So we have yet to put it on a computer in such a way that we see that happening, but it should be. Put it that way. So just to end, I wanted to mention this was from 20 years ago. There was a conference in honor of Lou's 60th birthday, which I was honored to be present at. My father was also there. He passed away 10 days ago, so it's special for me to mention that. And I hope that we will, in another 20 years, have another conference. Wishing Lou many happy, healthy, and fruitful years. Thank you.
Thank you very much.